Hello everyone, can you hear me? Hello. Okay, so good. We have 27 people, 28. I'm a bit worried. I think we have not many people as before, but okay. So today we'll keep talking about. Give me a second. Well, obviously the presentation is already on our website. It's already here, and we're almost finished with the term. I think we have only this session and two more, and we finish, right? So it's a bit sad. Okay, so we will keep talking about accelerating ray tracing techniques. And specifically, we will keep talking about Octrees. It is basically what we were discussing before. This regular grids, right? To this space partition thing. And we will also talk about other strategies to basically uh, solve the same problem or space partition problem. So BSP trees, which these are binary space partition trees, KD trees, rasterization, which is a different idea, and someone on the previous lecture was already like having that idea, which is actually very nice. And also we will talk about RTX technology, basically like how this ray tracing is done in NVIDIA in real time, right? The RTX technology. So yeah, so hopefully we can cover everything. Okay, so the our last session we were talking about this, right? The ray box intersection and this ray stepping algorithm. I I hope everybody already is convinced that this is a very nice algorithm and it's very cheap, right? And just a very quick clarification on the slides for our previous lecture, the equation for the intersection was saying that it was r prime minus r times k, which is actually correct, but I was omitting a step that is basically just adding the origin. This is not as this happens sometimes. We sometimes omit those things when we are talking about vectors. But yeah, I one of my TAs told me that yeah, it will be maybe better to make it clear. So remember, every time we're dealing with vectors, vectors start in zero, so we always need to add the origin, right? So I'm already changed the equation on the slides, so the slides are fixed, and I also modified the video. So yeah, so basically everything is good now. So we were discussing this, right? To basically take our space and basically segment our space, right, in a regular grid, and we can do this ray walking algorithm, right? And this is very cheap. So today we will talk about different strategies of space partition strategies, but different. And so the first one is BSP trees. These are binary space partition trees. So the difference with this is instead of creating a regular grid, right? You take your scene, imagine that you have something like this. We have a lot of dragons, and remember each dragon has probably 500,000 triangles. So you need to, right, to divide everything. So basically what you do, is you create planes to divide the space. So you start recursively divide your space using planes. The key idea behind BSP trees is that objects that are basically on the same that are not in the same side of the plane, right? Yes, Peter is asking support vectors. Yes, this is very similar to support vectors. Exactly. Yeah, support vectors is something that it's a concept for in machine learning. So yeah, basically. Oh, why you are saying oh no? Okay, Peter's saying oh no. I don't know why you're saying oh no, but yeah, it is very similar to support vectors. It's not exactly the same, but yeah, basically you take the space. I don't I don't support. What are support vectors? Okay, yeah, people is asking what are support vectors. Yeah, the thing is sometimes these type of things are related with machine learning. We don't have enough time to go in deep and explain those things. So for now, just imagine that you have the space, and according to a certain rule, you divide your space using a plane, right? What are those rules? Well, it depends. So, for example, in this case, you can take all the triangles on your scene, right? You have the coordinates of everything, right? So you have the coordinates of all your triangles on your scene. You can find, for example, the mean values, and or you can use clustering strategies to basically like divide all these objects, all your triangles, basically into groups, and and um, and yeah, basically you create this plane. Again, I don't want to get in deep into this into the algorithms on how you divide the space, because we will just literally spend a lot of time, and you will see that in the end we probably don't need to talk too much about this. So instead of the idea is basically, instead of just segmenting the space in a regular grid, you just recursively segment the space every time by half by half by half. I mean, half is not exactly half, right? But just like half space using the planes. And on every level, you're just recursively split the space using these planes. So the way you traverse a BSP tree in the end is you have your ray, and as you can see, every step that I'm drawing here, the lines have different width, right? So this is basically the first level. So we have two separate spaces here, right? So this is the second level, and the divisions have uh, the width is thinner, and obviously the color is also changing, right? So in every level, I'm just modifying so you can perceive what is the first one. So the way you basically traverse this space is, because you have a plane that is dividing on every space. You have a plane that is basically dividing the space. It's fairly easy to see which of those spaces is basically closer to you. So in this case, I have my ray here, or the origin of my ray here. And the one that is closer to me is this one, right? This half is the one that is closer on the first level. So then I can just go to the next level. So the next level is this division. So which one is closest? This one or this one? Obviously this one is closest. So this entire section here is closest, right? So once I'm there, right? I can go now check the next level, which one is closer. So this space is closer, right? And still there is no intersection, right? So there's no intersection there. So I go to the next one. So once I finish, for example, checking the closest one, I can go and check the farther, right? So now I check this one. And in this one, there's a dragon. I check if I have intersection with the dragon. If I find the intersection, that's it. I stop, right? And yes, David has a question. Give me a second. And give me a second, David, because I don't have my headphones and I need to. Give me a second.
Yeah.
Give me a second. Yes, can you talk?
Yeah, I can talk. I'm just wondering. So is BSP tree a type of space a space
Space partition?
partition method?
Yes. Actually, BSP means binary space partition trees.
Okay. Then what's the name for the previous one we were doing? I don't see a name for that. It's like you said, it's into a box. And
We use
is there a method?
there two. You can call it in two ways. Probably the correct one is Octrees, right? Because we are also dividing the space, but now in regular, right? In regular sections, and we usually split it in 8 pieces every time we are creating a different level, or just regular grids. Sometimes we just call them space partition or regular grid space partition. That is also another
Okay.
name.
Thank
Right?
you.
But yeah, this is a space partition technique. So the difference is instead of having a n number of cubes, right? You know, regular grid. And sorry, let me just. Can you mute yourself? Thanks. So so instead of that, you just create different levels of separation, and every time you basically split the space in two on each level. So what do you think are the advantages of this? What do you think is the advantage? Yeah, it's similar. It's similar like clipping. And someone is asking, will this algorithm get something like a cross shape, which we can identify which part is near? Yeah, of course. It can happen that depending on depending on the shape of your planes, or yeah, how they are basically constructed, and the direction of your ray or the position of your ray, it could happen that there is no closer section. In those cases, you just choose random, and it doesn't matter, right? Um, so somebody saying, gonna go on a tangent and guess this is a similar approach to divide and conquer. It is a similar approach to divide and conquer, yes. But think about advantages in terms of like complexity, right? So think about memory. What do you think about memory? What do you think it's better? What is more efficient, a tree or a regular grid of, I don't know, let's say 100 by 100 and by 100 cubes? Because remember, I mean, in the case of the grid, right, some of those cubes sometimes are just empty, right? Yes. So someone is saying depends on the amount of objects in the scene. Yes. Very good, answer. Yes. And depending on the arrangement of the objects, exactly, yes. So depending on the number of objects you have and where those objects are, right? Because imagine that, I don't know, somehow your scene is very irregular, and you basically have one object on each grid, right? Let's talk about the other option, right? The grid one, the regular grid. If you have literally one object per grid, well, that is not bad, right? In the end, probably they will behave almost the same, right? Either if you use a tree or not. But if you have, I don't know, maybe the majority of your objects are basically concentrated in some certain areas of your scene, right? A BSP tree will probably be better in terms of memory, right? Because you will need to reserve less memory to store everything, right? The other way around, you just need a huge matrix, right, to store all those cells in which maybe you have objects or maybe you don't, right? And of course, this obviously depends also in the way in which you specifically implement this thing, right? Because you can use arrays or vectors or pointers, things like that, right? But yeah, that is one of the advantages of using BSP trees. And it depends, again, obviously, the way they are arranged, right? What do you think are the disadvantages of this? What do you think? And think about the type of things we do in computer graphics, right? You trade memory, this takes more memory, less regular blocks. Yeah, well, I mean, one clear disadvantage with the other option is that the math we use in the regular grid case is very easy, right? I mean, this thing of intersecting with the boxes, you already see that it's incredibly cheap. This stepping or this incrementing intersections is also very cheap. And in this case, you're splitting the space in irregular shapes, right? So yeah, it could be a bit more complicated. And someone is saying also, if the camera changes the position, you have to recompute the entire grid, or any object moves for that matter. Yes, very good observation. Exactly. That is the most important disadvantage of this type of space partition algorithms. In particular, not the camera. If all the objects are basically static, and you only move the camera, it's actually not that bad. The problem is when objects move, right? This is a huge problem, because constructing a BSP tree is actually not as cheap. It's a bit expensive actually. All the other algorithms you need to use to define exactly where you need to put your planes and everything. I mean, you can actually use, for example, artificial intelligence or that data science approaches as SVM, as someone was already talking. But in the end, it's not super cheap, right? So if the objects are moving, right, if this is an animation, that is a huge problem, because basically a single object that is moving, you need to basically recompute the entire tree, right? So that is actually very bad. So these strategies, for example, are very good, or are good for static rendering needs. So, for example, something that is very common in computer graphics is to make architectural rendering, right? So when someone needs to create a building, right, before selling the building or a house or something, you create a 3D version of that. That is actually very common. Actually, architectural rendering, it covers at least. Okay, let me tell you a quick story. A long time ago, 13 years ago, I had a company. I had a render farm in Mexico. I'm from Mexico, and at that time, it was the first render farm in Latin America. So we had clients mostly on Mexico and a lot in I don't know, Argentina, Chile, and things like that. We have a couple of clients in Europe and United States, mostly small companies because we were a small company. But it was surprising for me that we had companies that they were doing movies and VFX and things like that. But the most of the work was incredible. Was architectural rendering. So architectural rendering. Okay, are you? Architectural rendering at that time, I think it was taking probably 80% of the entire 3D animation production of the world was probably exclusively architectural rendering, and it's a yeah it's a lot of work, right? So if you have scenes like that in which basically you're just rendering I don't know, the interior of a house or something like that, and you have a lot of obviously a lot of objects with with a lot of triangles. Usually the architectural scenes are very, very complicated, very sophisticated with very realistic materials or things like that. This will not be as bad because in the end, the entire space partition happens just at the beginning, right? And if anything, if basically the only object that is moving is just the camera, that is perfectly fine. But if you're talking about animation and you have characters that are basically like running or moving in the scene, then you have a problem, right? Because you need to literally compute the entire space partition every time, which in the case of the regular grid is not the case, right? If in the regular grid, if you have an object that is basically moving, only locally, you only need to change the you only need to change for that object that is moving, right, to which cell is now right? Basically, like every object belongs to a specific cell, or maybe two cells, because an entire object could maybe occupy the space of two cells, for example, or three, or whatever. So you just modify the like who is the owner of that object in particular. So it's obviously cheaper, and you don't need to recompute everything again. And someone was also asking about the advantages again. Okay, the advantage is if the scene is not totally crowded of objects, right? If you have a scene in which you somehow have I don't know, like huge volume of space, or some areas of space that are almost empty, and your objects are kind of like concentrated in certain areas. In that case, you will probably use less memory, right? Using a tree than using a huge data structure that is basically have this grid, regular grid, right? And someone is asking, what about purely orthogonal planes? Very good. So basically my lecture presentation is almost in the same order in which you will think about the answers. So yes, so that is actually another type of BSP tree called KD trees. So Peter is saying, what about purely orthogonal planes? That is actually a KD tree. So in this case, it's exactly the same idea, KD trees, but in this case, the planes are axis aligned. And the way you split the space is by you first split in the x-axis, then you go to the y-axis, then the z, then again the x. So for example, in this case, because it's 2D, you basically split in x-axis, then y, then x again, then y, and you just keep splitting the space. And someone is asking, can you explain objects on the same side of plane as viewer? Okay, give me a second. So basically the idea of that is you need to imagine that you have spaces, the space sections, right? And you have a viewer. So imagine for a moment that the ray is basically the viewer, right? The ray is also moving on this space, right? So the viewer in this case is here, right? This is a camera. Let's say that this is the viewer. So the viewer is on one side of this plane. Let's talk about only this plane right here. So the idea here is that it is, if you are on this side of the plane, it is impossible to be occluded by objects that are on the other side of the plane. That is what that phrase is telling you, right? So you can be only occluded from objects, right, that are on the same side in which you are, right? That is basically the thing. Okay, so let me go again here and let me check what are you writing. What if there is no plane that we could make that wouldn't cut through one of the objects? What do you mean? I don't understand that question. What if there is no plane? Yeah, I don't understand. Why do you think there could be no plane? There's always a possible plane, right? So again, remember you have the coordinates of your scene, right? You have the coordinates of, for example, all your triangles. And in particular KD3, what you usually do is you find the mean value, for example, in X. So you create the first, you take that value to basically cut everything in half, right, on X coordinate. And then you go and for each two pieces, right, each of those two pieces, you basically repeat the process, but now getting the mean value now in Y, and you create, right, this section and then this section, and you just again repeat the process. I'm not showing every segment here. For example, I'm going deeper in this area. I didn't show like divisions here, right, because it's just an example, right? And someone is saying there is an unlucky dragon that is cut in half near the bottom. Yeah, it is on purpose. So what do you think we need to do in that situation? What if you have an object that is basically cut it in half by one of those planes? What do you think you need to do? Clip triangles, that is one option. Yeah. Do more partition around the dragon, that is another option. The thing is, depending on the object. So imagine that it's an object like the dragon, right? So the dragon is made out of thousands of triangles, right? So in the end, I mean, even if it's a single object, right? Because it's a single dragon, what you do is just take, right? Like the triangles that are on one side will belong to that side. The triangles that are on the other side will belong on that side. And only for the triangles that are basically in the middle, you just clip them. You can clip them, right? You just divide those and basically you split the dragon in two. If you have a different type of model, because this is a model that is made out of triangles, right? But maybe it's a sphere, right? The type of spheres that we were using are implicit spheres, right? Because we were not using spheres made out of triangles, right? We have spheres that are just basically math information, right? Just the geometry of the sphere, the center and the radius, right? So, or to have like an implicit sphere. In those cases, what you do is, if a plane of the KD tree is basically passing in the middle of one of these objects, you cannot split the object, right? Because there are no triangles. So what you do is just you kind of duplicate the object. So basically, the object will be on the list of one side and also on the list of the other side. And in the end, eventually, the ray will hit only one of those sides, right? But in the end, what happens is that it will be duplicated, right? The object that is basically in the middle of a plane, it will be just duplicated. Remember, in the end, these trees are just like nodes, and every node is like a vector of pointers. So let's imagine that this is a node, right? Well, this node in particular will have a vector with two pointers. One is a pointer to this object and the other one is a pointer to this object, right? Because in the end, that is what you need. You need to get your ray and tell your ray, oh, there are two objects in this space, or three objects, or two triangles, or three triangles, or whatever, and just, okay, here's the information, check if you're basically intersecting with those, right? Okay. And what do you think are the disadvantages of KD trees? Yeah, I mean, if you need to clip triangles, that could be a disadvantage, of course. Get too much duplicated dragons, yes, that is actually also a bad thing. Although you're not literally duplicating the models, right? So when I said you need to duplicate the dragons or duplicate the spheres, you're not literally duplicating. You're just duplicating the pointer on those lists, right? So for example, this dragon in particular is basically is in between three leaves of the tree, right? So this leaf has its own list of pointers. This one has its own list of pointers, right? So basically, the dragon pointer is duplicated, right? Because it's on this leaf and also on this one and also on this one. So you're just duplicating a pointer, not duplicating the entire thing, right? And someone is saying some areas have many objects. Yes, that depends on how. That depends on where do you stop, right? It's a very good observation, of course. So this is, we also discussed this when we were talking about last lecture. We were talking about the regular grids, right? So the thing is, how do I determine the size of my grid, or how many levels I have in my Octrees, right? How much I go deeper, and creating like small things. In this case, it's also similar. So usually in either BSP trees or and KD trees, remember, KD tree is a type of BSP trees. Usually you have a threshold of, for example, if you're talking about triangles, right? If your geometry in general are triangles, you could have a threshold of a certain number of triangles inside your leaves, right? So basically you will recursively cut your space, right? If we are talking about KD tree, remember the cutting planes are axis aligned, so you're just recursively cutting, and you will stop whenever your leaf has a certain number of triangles. So you say, okay, I will stop when the number of triangles in the leaves is it's I don't know, less than whatever 200, right? Okay, that's it. You will end there, right? And yeah, so but it's true, right? So depending on how you define your stopping criteria, you could have leaves with probably a lot of triangles, right? And someone is saying less flexible than BSP. Yes, that is one very specific disadvantage between KD tree and BSP, right? Because in the end, because you're constrained to be axis aligned, and again, this is depending on how your objects are distributed on the scene, right? But there, sometimes for a certain distribution on objects, you could need to cut in more pieces with a KD tree than a BSP, right? Because KD tree is just constrained to be axis aligned, right? So sometimes you just need to cut in more pieces, while in the case of BSP, right, you have more flexibility to choose exactly the plane that you are using to cut, right? The advantage of KD tree with respect to BSP is that it's a bit less expensive to construct the KD tree than BSP, right? Because BSP, because your cutting plane, right, you require more information to basically decide where is your cutting plane, because it can be in a diagonal and things like that, and And in case of KD Trees, is way cheaper, right? Because it is axis aligned. Just take the median and just cut there, right? And the other disadvantages that the KD tree has is basically the same as the BSP trees. If you have moving objects in your scene, this is a bad idea, right? Because every time something is moving just a little bit, you need to recompute the KD tree again, and that is obviously very expensive, right? And so when he's saying, can you switch between BSP trees, Octrees, and KD trees depending on how your objects are positioned in space, or do you normally stick to one? Very good question, and that's what I want today. I want today for you to think about these possible solutions. Yes, combining different strategies is sometimes interesting. The thing is, in the end, you need to see what is the most the fastest solution, right? So Octrees, remember the advantage of Octrees is that you can have objects that are moving, and you don't need to reconstruct the entire Octree again. They're just modifying the information, right, of the object that is basically moving. But BSP and KD trees, they need to recompute it, right, from scratch every time something is moving, right? So the thing is, yes, combining things is interesting. So you're right. The thing is, where do you combine those? And you will see when could be interesting. But yeah, that is something interesting. Okay, and someone is asking, what is AABB? Do I have ABBB? I don't have ABBB here, but AABB, sorry, means axis aligned bounding box. Oh, someone is already answering. Yes, axis aligned bounding box. Yes. Yeah, axis aligned bounding box. That is the answer. Sorry. Okay, so someone, the previous lecture was saying, okay, what about rasterizing my scene, right? So can you remember me? Who was the person who was saying that? Who? Tommy. Okay, yes. So Tommy had this brilliant idea. Why I said it's a brilliant? Because it is. The thing is, the problem that we are trying to solve here is we are shooting rays from the camera to the world, right? So remember, this is in general called back tracing, right? And Tommy's saying, oh my God, stop it. And so that is basically the opposite of what happens in real life, right? Because in real life, rays are coming from the light, right? So light comes from the light source, is hitting the objects, and then it's bouncing to the camera. So the idea of ray tracing, the idea of forward ray tracing, of shooting rays from the light and then getting to the camera, is very old actually in computer science, very, very old. But it was something that people thought it was just unsolvable. It was like, oh no, but that will be incredibly expensive, right? People had absolutely no idea how to compute that, how to have a good solution or a good approximation of shooting rays or beam light beams, right, from the light, hitting surfaces and then bouncing to the camera. Until someone in, I think it was about 1968, had the brilliant idea of saying, okay, why are we trying to solve this problem from, let's say, A to B, right, to light to the camera? Let's just do it on the opposite way. Just invert the problem. Now let's try to shoot rays from the camera, hit the objects, and then to the light. That it's an absurdly simple idea, but nobody thought about that for many years, right? Until 1968. So in this case, we have a similar problem, right? But we are sending rays, right, for each pixel, and somehow what we need here, right, to accelerate our ray tracing process is, I need to know which pixels are basically not touching anything, right? Which pixels are just getting, let's say, the background color, and which pixels have some objects on its way, right? But with these space partition techniques, we are seeing the problem from the camera to the objects. So a brilliant idea is, okay, what about just doing backwards? What about iterate each object, right? And now see the problem as, okay, now let's tell the objects to tell the pixels, right? okay, I belong to you, right? That is something like that. So it is an interesting idea in terms of how do you solve problems. So that is basically rasterizing the objects, right? So rasterizing the object means to basically project your objects. So let's check this very simplified version of the scene. I just removed the dragon. Let's imagine that we have only spheres. So the rasterization, if you remember what was the rasterization, is taking information that is continuous and just modify project that information into your 2D screen, right? It's basically deciding which pixels of your image belong to specific objects, right? And rasterization is on this direction, is from the object to the screen, right? So it's similar. Imagine that these are spheres, and imagine that for each sphere, rasterizing the sphere is like constructing a cone. Imagine that this is a cone, and getting the intersection of that cone with the image plane, right? You will basically get the projected version of this sphere right here, and you will be able to see exactly which pixels are covered by that sphere. You agree? So this is basically what could happen, right? So so I can iterate only once, right, per every object. And now I have exactly which pixels are corresponding to each sphere. If I do that, I don't need any space partition, right? Because now every pixel in this area, I don't need to do anything else. These guys, they just get the background. These guys, they don't need to explore anything on space. They just directly go and check its intersection with this sphere. These guys right here check the intersection of this sphere, right? So every blue pixel is just getting the background, and everything else has just like a pointer, right? So in this case, the pointers are now kind of in the pixels. So every pixel has probably a list of pointers pointing to which objects are seen, right? So what do you think about the advantage of this? Can you mention any other advantage you see? Someone is saying if you have parametric representation of objects, then you can get parametric representation of the intersections. Yes, that is a very good observation, of course. Okay. What else? In sparse scenes, save a lot of time. Yes. Again, depends on each scene, right? So, yes, this is very true. If the scene is very sparse, right, and the objects are very simple, right? Because in the end, I mean, if you have 2 million triangles, right? Imagine that these spheres are not these are not implicit spheres, but spheres created by triangles, and maybe you have, I don't know, 2 million triangles on each sphere. In that case, it will be a bit complicated, right? Because rasterizing 2 million triangles is also complicated, right? Somebody saying save space on internal representation of objects. Yes. I guess you could project bounding box. Yes, exactly. So if you have very complicated objects, you can project the bounding box. Exactly. So if you rasterize the bounding box, this is a good idea, Peter. If you project the bounding box, it will be very cheap, right? So in the end, okay, you have a certain region of pixels that you know they belong to this object in particular, right? And that's it. There is no space partition. Okay, so I think everybody agrees that this is actually not a bad idea, right? So now let's talk about possible disadvantages, because there are a couple of disadvantages. So imagine that you have something like this. If you have a lot of objects that are basically on the same direction from a specific group of pixels, in the end, when you're performing this rasterization, right, you're kind of collapsing the problem. The problem of space partition problem. You're collapsing the problem now, and you're kind of removing one dimension, right? So I have something like this. Basically, it could be the case that all these objects are basically intersecting the same pixels. So many of these pixels, or maybe the majority of these pixels, they don't have a single object on their list. They could have thousands of or millions of objects in their list, right? So in that case, those pixels will be very, very slow, right? Because they just have the information of, okay, yes, I have this 200,000 spheres, but in the end I need to go and check all those intersections, right, from my ray to all those 200,000 spheres, and check which one is the closest one. And you could have even objects with um, opacity less than one, right, transparent objects, things like that. So yeah, it is, the algorithm is not perfect, right? You could still have a lot of problems if there are a lot of objects that are basically colliding in the same tiny space of specific pixels. And somebody's saying, why should this matter if the object nearest to the image plane would block the light? Yes, that is true. If the closest one is blocking the light, if the closest one is not transparent and is blocking the light, that is true. You need to stop here, but you need to know that this one is the closest, right? So you need to add into this algorithm, besides the rasterization, you need to add depth. Exactly. Someone is already saying, use depth graph. Exactly. So you need to add depth, right? Yeah. Great. I think everybody is agreeing. So this idea is actually very good. If you add the depth thing, it's actually very good, and it's very good for primary rays. However, for secondary rays, it could get a bit tricky, and actually could be even worse. So remember what are the secondary rays, right? So for example, if we are doing, instead of only ray tracing, if we are doing path tracing, it means that for every intersection we get, instead of just computing, we get into this intersection right here, instead of just computing the bling, let's say a bling equation using the light, no, that is not what we want. In path tracing, if we want to fake global illumination and color bleeding and all that thing, we need to shoot a lot of random rays from this point, right, into different directions to my scene to get basically the average of all that, because every object is considered as a light and every object should contribute to the color of this one. Remember that? That is path tracing, right? That is the idea of global illumination of path tracing. So the thing is, you will need to now rasterize everything for that tiny intersection. Do you agree? It's like for every new intersection you create, if you need to, from that intersection, to scatter a lot of rays, it's almost like, okay, now you need to almost like create a camera with an image plane and rasterize everything to that fake image plane, right? To take everything there, right? So in that case, if you add secondary rays, this idea will be probably probably way worse than space partition techniques, right? Because now you will need to iterate all the objects to rasterize all the objects every time you hit something, and you need to scatter things. And that this will happen with reflections, refractions, global illumination, color bleeding, and things like that, right? So yeah, it is a nice idea, but it's not actually a good idea for secondary rays. So it is actually used for primary rays. It could be used for primary rays, but for secondary is not that good. Okay, so now let's talk about possible disadvantages of Octrees, right? Because the idea we discussed the previous lecture was this, right? Creating regular grids, basically, it could be Octrees or regular grid. So one disadvantage could be, for example, this. Imagine you have something like this. You have just a enormous triangle that is basically passing through a lot of cubes, a lot of squares here, or cells, right? And so it means that this ray right here, there's no intersection between this ray and this triangle. However, because this triangle is basically on the list of almost every single cell, every time I'm stepping, right, I'm walking my ray into these into these squares, every square is telling me, oh, I have a triangle inside. This is a triangle. So now I need to compute the intersection between the ray and the triangle, right? So if I do that, every time I get into these guys here, it will be incredibly expensive, right? So the good thing is the solution of this problem is very easy. So we usually need to tag objects. So if I get into this one right here, and the first cube is telling me, oh, I have a triangle, and this is the triangle, and I check if I am hitting that triangle, and it turns out that I'm not hitting the triangle, I take that triangle and I put it on a list, or I put a tag on that triangle saying, I'm already checked you and you're not, right? It's like saying, I'm already know that that I don't hit you, right? So I go to the next one, and if this guy tells you, oh, by the way, I have a triangle, if that triangle has that tag, okay, I don't do anything, right? So I just go directly, right? So this is a disadvantage, but it's actually very easy to solve. Another disadvantage that we already talked about is how small do you need to create your grids, and that is actually something very complicated. We were discussing that at the end of the previous lecture. So you could again, you could say, okay, I will just keep splitting, right? Like splitting my Octrees, or creating different levels of my Octrees until I have squares that are tiny enough to get, I don't know, a certain amount of triangles, right? So if you have something like this, I have 500,000 triangles in this small dragon, I will need to create a huge data structure, right? Because I need to a huge data structure, Octrees, or a lot of division, right? A huge amount of memory that is just reserved there, almost empty, right? Only to compute this tiny guy. So what we do usually to solve this problem is a possible solution to this is basically to use a combination between a global and local partition, and that is exactly what someone was already saying, right? Like combine things, right? So you could have a coarser regular division or coarser octrees. I mean, you could even have different levels. So you could have, for example, maybe only 2 levels, right? Only 2 levels with certain size, and then the object itself could have its own local partition, right? And its own local partition could be either an octree, or this local partition could be, depending on how do you need it, it could be also a KD tree or BSP, right? So it could be anything. But let's say for now that you have a local regular partition for your dragon and also a global partition, right? So that will be actually very efficient, right? Because everything is regular, everything is fixed, it's super cheap, and also because this partition is basically, imagine that it's like a stick to your model. Even if the model is moving or rotating on, right, any transformation you have to the model, well, the space partition thing is also transformed, right? So imagine that you're traveling with your ray in this grid, and it's very cheap. Remember, it's super cheap. You're just stepping, right? You step in this one and then this one. You find out that in this cube right here, you have this object. So then you go into the local space of this dragon, and because you have the transformation of this dragon, you just apply that transformation to your ray, and now inside this local space, you will have your ray in the local coordinates. So you will have everything axis aligned to this tiny space, and you could basically repeat the same algorithm that we saw last time, right? Everything is regular and it's super easy to walk your ray. And once you find the correct intersection, you just apply a reverse transformation to that intersection, and that's it. And everybody's happy. This is actually very convenient, and in the end, this is a combination of having different bounding boxes or different subdivisions for objects. It's also called bounding boxes. Bounding boxes is BVH, bounding boxes hierarchy. So that is actually a very, very nice idea. So questions. Since we have talked many advantages and disadvantages for different methods, would it be possible to have a summary table to conclude on that? That is a very good question. I want you to take notes, because this could be today's lecture. I wanted to think about these disadvantages or advantages. So that is very nice, and maybe you can start that table. Yeah, that is actually a very good idea. And but yeah, you need to take notes, right, about this, because this could be questions, right, on your final exam. Okay, so I think we need to end here. I still have a couple of slides about RTX technology, but we need to end. One of the feedbacks that I got in the survey is that some people was not as happy of having lectures that are getting more than 50 minutes, and because I understand people sometimes need to go to check other stuff. So let's stop here. Next time I will talk about this. I will talk about um, yeah, because otherwise I will need to just keep going. What do you think? Let's vote, because it's 52. Do you prefer to just see this on Monday on the next lecture? I have maybe like 5 more slices or 6 more slices. Or do you prefer to just continue? Say yes if you want to continue. Yeah, and remember, I mean, if you need to go right now, you can go. Just you will probably need to go then later and check on YouTube the last 15 minutes or something. Okay, so let's continue. Okay, so how people on Nvidia do this on real time, right? Because it seems almost miraculously when what they are doing. So they are doing reflections, right? They are able to do reflections, real-time reflections, real-time uh, ray tracing reflections. They also can perform global illumination, right? And by the way, they use BBH technology or BBH approach. That is exactly what I just said. Bounding, bounding volume hierarchies, right? Um, so remember, global illumination is this thing of path tracing. Every time you hit something, you just throw rays to different directions to get a contribution from the objects that are basically around. So this is already possible in NVIDIA, right? In this technology, and you already know that this is incredibly expensive. Even using space partition techniques, it is still a lot of competition. So how these guys are doing this in real time? So there are many tricks. So one of the tricks they have is, let's see this scene. I think this scene is from Battlefield. So we have this impressively realistic reflection here. So one of the things they do is they do something that is called adaptive sampling. Adaptive sampling is, instead of just throwing a lot of rays every time, right? You will restrict your rays only for the areas you need the most, right? So for example, in this example here, you have, because you have the information of your materials, you know which materials are more reflective than others. You only throw rays on the most reflective materials, or the ones that are actually needed, right? So basically what happens here in this type of shading is, you already noticed that, for example, computing bling is super cheap, right? You have, if you compute bling or phone equations for an object, you're faking reflections. You're not really computing contribution, like global contributions. It's just fake. So basically what happens here is you decide in real time, depending on the material properties, which materials you could fake and which materials you need to use ray tracing, right? Instead of just ray trace everything, right? So this is called adaptive sampling. And this technology of adaptive sampling is not only for real-time ray tracing or real-time path tracing. This is also used in other tracing engines or path tracing engines. So for example, I made this image in V-Ray. V-Ray is one of the render engines that you could use in Trees 2 Max. And this image has a lot of objects, right? I mean, every particle here is a separated model using a particle generator in Trees 2 Max. And the material of these particles is very complicated. The materials are actually refractive. Some of these, because it needs to mimic sand, right? And sand, you have different materials on sand. So some of those are almost transparent. Some of those are like more milky mineral things. Some of those are almost like gold things, right? You can see this on the reflection here. And so this scene right here is very complicated. So you can tell V-Ray to use adaptive sampling, right? So use these rays for all these effects that you have in your scene, either reflection, glossy reflections, depth of field, everything. to just distribute the amount of samples, distribute the amount of rays in the areas in which you basically need more, right? So blue is almost no rays or less number of rays. And you can see from blue to green, yellow, and red, right? So the red dots are the ones in which V-Ray decided to throw way more rays, right? So this makes the render incredibly cheaper, right? I mean, it takes still a lot of time, but it's obviously cheaper, right? So you have these strategies of adaptive sampling, and again, depending on the material that you're using, right? So that is what they do. They basically have three main strategies. They have bounding volume hierarchy setups, which is exactly what we talk about, this space partition techniques, right? And they have ray triangle intersection techniques that are basically adaptive. They have like very efficient ray triangles intersections, and they have efficient algorithms to decide where they need to send more rays. But they have another trick behind the curtains, which is denoising. That is probably the most important thing that they actually do, and this is a bit or this could be a bit disappointing, because what happens is, in the end, they are not really doing like a complete path tracing. So what happens is, this is actually how an image looks when the path tracing in real time happens in a image in real render time in RTX. This is actually the final image after the path tracing. What they do is they just throw just a few amount of rays, not too much. You're already probably working on your ray tracing assignment, and you will see already that if you reduce the amount of rays that you're shooting, your image will look very grainy, right? If you don't want your image to look that grainy, you just need to add more rays, right? So yeah, just if you remove the amount of rays you're sending to the scene, right, dramatically reduce the amount of rays, the image will look horrible, like this one, just super noisy, but it will be very fast, right? Because you don't have too much rays to compute. So the thing is, artificial intelligence, specifically deep neural networks, are very capable since a couple of years now. They're proven to be very good to improve images like this one, basically to remove the noise. So you just take this image and you apply artificial intelligence techniques, denoising techniques, and from this image you get this image right here, right? So this looks impressive, and it seems that you shoot a lot of rays, millions of rays. Well, it's not the case. It's just a horrible image that is then, with artificial intelligence, it's just removing the noise, right? So it's basically a combination of almost every strategy that we have talked about in the entire lecture, because here this is basically real time. So we are talking about the rendering pipeline that we discussed. So there is vertex shading here, fragment shader, there is rasterization, there's all those things. Most of the colors that you're seeing here, most of the color that you're seeing on each pixel right here is actually computed using either Boolean, Phong, or anisotropic equations. So it's kind of fake. And you're just adding a bit more realism, sampling just a few rays, right? It will generate a lot of noise. Then you go and get a neural network, denoise that information. You combine the denoise information with the real-time information that you already have with Bling and Phone things. You combine those things and you get this amazing result, right? So it is actually just very clever. And the way they are also doing is just by modifying the hardware. So what happens in modern computer graphics GPUs, right? What happens in modern GPUs is that they just created separated cores for almost and someone is saying, is this computer graphics? Yes. I don't understand the question. Yeah, it is computer graphic, of course. So what they did is in the modern GPUs, they are just creating more dedicated hardware chips right inside the GPU. They're just like exclusive for certain areas. So for example, this is a Pascal technology. So in this Pascal technology, this entire part of the graph is the ray tracing the ray tracing computation. It's huge. It's basically 80%. 80% of the entire computation. This is a single frame. This is a single frame of a scene using ray tracing, right? And almost everything is basically covered by that. So the next technology they created was Turing. So in the Turing technology, what they did is they created a new different type of cores. Now they separated for Turing. They separated cores that are exclusively for floating point computation and cores that are exclusively for integer computation. And so basically, they compute any integer computation with any floating point computation at the same time. So that is what you're seeing here. Basically, the purple graph here, the purple things are integer computations that are happening at the same time of the floating computation. So instead of right before they were just computing on the same hardware, now because they're split it in different hardwares, you can basically compute it at different times, right? Then they created for the Turing RTX, so basically the latest technology they have, they created new type of cores exclusively dedicated to you to do ray tracing. So instead of using the regular cores for the ray tracing, now you have a separate group of specific cores exclusively for ray tracing, and that is this spike right here. So basically you are just compressing, right, almost everything related with ray tracing. You're compressing in a very small amount of time because you just have a lot of cores that are exclusively dedicated for that. And then they add tensor cores, which are basically cores dedicated to compute deep neural networks, basically AI, right? So the denoising happens here. So all the green thing is computation that is regarding artificial intelligence, basically the tensor cores, right? So in the end, it's just let's throw more hardware, dedicated hardware, compress it in the same card, and that's why we have this amazing stuff. Okay, so thank you so much. I think we need to finish for now. Remember that if you haven't done this, please go and take a bit of time. It's very important for us. It's very important for the department, for UBC, for the TAs. You need to yes. I mean, it's not mandatory, but it will be great for us if you have time to answer these student evaluation teaching survey. Good. Thank you so much, and I see you on Monday. Bye, everybody. And someone was asking, will we discuss about midterm too? Yeah, if you want, maybe we can discuss about that maybe on Monday. Yeah, I can maybe reserve a bit of time for that. Yeah, sure. It's already there. If the grades are already there, by the way. Thank you. Bye.